Okay, so let me share the content. Okay, you can see the slides. All right. Okay, so in our last class, we have covered up to deal growth model. Okay, so the previously discussed this deal growth model. So where there are three main steps involved in the model. So let me just go back to the steps. The first one is on the gas transport flux, where you have your oxidant, either it's from a dry ox process or a wet ox process, sent into the furnace before it starts the reaction with the silicon wafer. And then diffusion of the flux through SiO2 as the process builds up. So the reactant or the oxidant has to diffuse through the oxide at whatever thickness to be able to reach the silicon interface underneath. And then the third step, there'll be reaction of the oxidant with the silicon to further develop the thickness of the SiO2. So we have looked at the derivation. We have looked at what is F1, F2, F3, all the fluxes for all the three steps. So it will become clearer as you do the calculation later on. So possibly your assignment one will be covered with the growth model as well. I'll get back to you on your assignment one later on. So now let's look at the oxide on wafer topography. So we have looked and we have discussed that when you do the thermal oxidation process, the process is going to consume your silicon to be able to grow the oxide. So it's 54, 55, 45% rule. Some say 54, 46, but it's somewhere there. So part of your silicon will be consumed to be able to grow your oxide. So if you look at this slide, for example, you look at the first one. If you start off with a bare silicon on the top left is your bare silicon here. Okay, so if you do the oxidation process, whether it's dry ox or wet ox, so you're gonna be end up with silicon dioxide on silicon. Just imagine that if you have oxide on the top surface, but actually it consumes the whole surfaces of your silicon. So that means when you do the oxidation process, since all surfaces will be exposed to the oxidant, so that means you have your front surface, your rear surface, your sides of your silicon wafers. So you're going to have your oxide on the whole surfaces. But here I'm going to show on what's happening on the top surface only. So just omit the other surfaces for the time being. But you have oxide on your other surfaces as well. All right, so you're going to end up with the SiO2 on your top surface. So as shown by the figure on the top right, so SiO2 on the silicon, no matter what the thickness is. So later on, we're going to go through lithography and oxide after this. So where you want to do your patterning on patterning of silicon dioxide on the wafer. So you can also do the patterning of photoresist. You can also do the patterning of a SiO2 layer on your silicon wafer. So the basis of doing lithography and etch is to enable patterning process. So so as we obtain a blanket, I mean the whole surface, blanket means the whole surface. Since we have obtained a blanket SiO2 on the top surface, so some processes after that might require patterns to be present on the surface. So therefore you have to do the patterning. So then how does the growth of silicon dioxide look like on a pattern wafer? So when you do the patterning, you want to keep some of your SiO2 on the surface, and you want to also remove at the same time. You want to remove some oxide from the surface, and you want to also keep some oxide on the surface. So you're going to end up with macam square shape ni lah, macam pulse shape lah. So what you have on the left and on the right, left and right here is what you keep, the oxide that you keep. So the middle here is the oxide that you remove. So how it's done, we're going to learn in the lithography and etching processes later on. So just imagine that you now can do the patterning. So the oxide in the middle region is removed. So you're going to end up with patterned oxide on your silicon wafer. So you're going to have your pattern on the left, pattern on the right, structure on the left, structure on the right, and the central region is exposed. So we call that pattern SL2. So what happens when you use the pattern to perform another oxidation process? So before this, we have discussed on growing SiO2 on blanket or on the pure or on original silicon wafer. So what if you have pattern wafers instead? So if you have pattern wafers on the bottom right, so you send the wafers to the oxidation furnace again. So look at the grown SiO2 on the pattern wafer. So you're gonna have your SiO2 in the central region as well. So maksudnya dia ada thickness dekat tengah tu. And then the very same thickness can also be obtained on the sides, on the left hand side here and right hand side as well. So maksudnya you're gonna have your structure like that, ketebalan yang sama, more or less. But the central one dia duduk kat bawah lah, sebab bawah tu mula-mula dia tak ada oxide to begin with, right? And and you're gonna have your oxide on the left and on the right as well. Okay. So just let's reflect on this process. If you relate your deal growth model to this particular process, doing oxidation on pattern silicon. So kalau you tengok dekat sini, if you grow your oxide on on the left and on the right in comparison to the central region, yang mana yang akan experience higher growth rate? Is it on the existing oxide or on the pure silicon? Growth rate yang mana yang akan lebih tinggi? What do you think? Let's reflect on the deal growth model. We're not talking, okay, okay, Hazik, are you saying it's pure? Pure is gonna be experiencing higher growth rate, right? Why do you think so? Why do you think so? Okay, can you unmute yourself?
Because there is no oxide in the silicon yet, so it is easy for the oxide to diffuse in the silicon layer.
Okay. So maksudnya reaction tu will be so reaction lebih senang, lebih cepat sebab there is no oxide to on the silicon as a barrier, kan? Is it?
Yes.
Okay, that's what Hazika said. Okay, any other opinion? What do you think? Anyone has another opinion? Hazika said it's faster on in the central region because there is no oxide to begin with. And the argument is no oxide, therefore faster for the oxidant to react with silicon. Any other opinion? Fazira, what do you think? Fazira, what do you think? Are you of the same opinion or different opinion?
Same opinion with Hazika.
Same opinion, okay. Chingwei, what do you think? Go Chingwei. Same opinion, all right. Anybody of opposite opinion? Inas. Inas, same or different opinion? No idea. Okay. Okay, kalau you tengok, well, let's recall Bill Grove model. If you look at the first step, bila oxide start reacting with the silicon, what is limiting the reaction? What is limiting the reaction when the oxidant or the oxide starts to react with the silicon? Apa yang limitkan reaction tu? Is it related to the oxide at all? Cuba tengok what's the limiting factors for oxidant to react with silicon versus what's the limiting factor for the oxide to react with silicon with existing silicon dioxide. Apa bezanya? What's the limiting factor? Amira, what is the limiting factor for the first one and for the second one from Bill Grove model? Apa limiting factor yang kita discuss sebelum ni? Yep, for the first step, the limiting factor is only the number of silicon atoms, right? So if you're talking about this particular silicon, so we are not comparing with other different orientations in this case. So there's no issue. So on the other hand, for the second step, what is the limiting factor? With the existing oxide on silicon? Liana? Anis Liana? What's the limiting factor for the second case? Oxide on silicon already there.
啊，就是你帮我啊，
Sama.
拿一点东西。哎，
Diffusion rate, right? Diffusion rate of oxidant through existing oxide. Okay, so it's limited by the diffusion rate. So secara logiknya memang the first one will be faster lah, sebab dia tak payah diffuse to the oxide. Kalau ada pun maybe very thin native oxide if you don't remove, but you have to remove beforehand. So even though the bottom left figure here shows the thickness throughout the areas is similar, tapi sebenarnya dia punya growth rate is slightly different. So maybe dia punya exact thickness is not the same because the rate for the central region is higher than the rate for the left and right regions. Okay, due to the different limiting factors acting at the same time. Yanni, you forgot to mute your mic. Thank you. Right, so kita akan dapat feature macam ni left and right, left, center, right. So if you have to work on your oxidation on patterned oxide on silicon, so this is how it looks like. Looks like after the process. Okay, you can actually manipulate this for your own step or device, right? So you can do this. Well, some cases might need you to work on blanket oxide and then you have something on top. Some other cases or some other steps might need you to have pattern oxide before you do anything. So we're going to see later on as we see how the other processes develop over time before you have your final chip. Okay. So take note of the limiting mechanism or limiting factors on this different region and relate to the Deal Growth model that we've covered before. Okay, if you if you have your oxide on your silicon, if you have something like this, oxide on silicon, and you want to see the crystal orientation, if you like, you send a cross section. So you have the SiO2 on silicon, you thin it down, you send the thin sample on TEM. So we've covered TEM last time on wafer characterization. It's transmission electron microscope. So you want to see the interface. So this is how it's gonna look like. So you're gonna have your amorphous silicon dioxide, typically amorphous, on monocrystalline wafer. So you nampak kan kat bawah tu dia crystalline orientation is very periodic of infinite length. Dia tak ada limiting dia tak ada limiting region. What if you see borders dekat region crystalline silicon tu, then what could be your conclusion? Sekarang ni you nampak infinite periodic array of silicon arrangement, atomic arrangement. Kalau tiba-tiba you nampak border and the atomic arrangement changes, what could be your conclusion on the property of your silicon down there? What does it mean? Is it still a single crystal? Anyone? Is it still a single crystal then? If you see borders or change of crystalline orientation in this particular image. Shahira. Is it still monocrystalline? Shah?
Yeah, I think no.
Okay, why? Why not?
Because the structure of amorphous and combination with monocrystalline.
Okay. My question is, so now forget about amorphous up there. Just look at the crystalline silicon down there. Sekarang kita nampak silicon atom, arrangement is infinite, right? It's throughout the image, right? And that is single crystal, isn't it? So what if dalam TM image ni you nampak ada changes of crystalline orientation dalam silicon tu? Is it still a single crystal? Zira? Yes means what? Still a single crystal?
Yeah.
Oh.
Yes. Because I just
Okay,
I'm not
why
add the
yes?
layer on, because I think just add the layer on the crystalline silicon. It doesn't.
Okay.
It's not crystalline silicon itself.
So is it okay? Kalau you nampak changes of the periodic array, so is it still crystalline silicon? You said yes.
Yeah.
Okay.
Yeah.
All right.
Maybe.
Okay. Thank you. Okay. What is other opinion? Shamim, what do you think? Forget about amorphous silicon on top. Just look at the crystalline silicon down there. So if, for example, kalau dalam TEM you nampak ada changes in the periodic array. No. Okay. Naim said no. Why, Naim? So no longer a single crystal. So why is it so? Then what do you call that? Yeah, polycrystalline, right? Kita dah belajar 386 kan? So the moment you see the periodic arrangement is disturbed or it's changing its array, maksudnya susunan dia dah tak sama, it's no longer infinite. Dia ada finite length je sampai distance tertentu, then you start seeing another pattern pula for some other distance and extending to some other region, then it's already polycrystalline. So in this case, it's single crystal because at least finite is no disruption in the lattice arrangement. So it's single crystal. So if you start seeing a change and another pattern emerges, so it's called polycrystalline. So in this case, it's amorphous silicon dioxide on single crystal silicon. Okay. So nak test you punya 386 last time. Kita dah belajar crystallinity of material kan. So this is how it looks like under TEM. So if you grow amorphous whatever your material, so it's gonna look something like that, like the amorphous silicon dioxide on top. You tak nampak arrangement kan? There's no atomic arrangement, right? It's just short distance arrangement and no periodic arrangement, no particular pattern. So therefore, it's amorphous in nature. So maksudnya kalau you dapat TEM image, then you can tell right away from this particular image, oh, atas ni actually is amorphous whatever. If it's silicon nitride, then amorphous nitride or some other material lah. But then you can already tell the crystallinity just by looking at the TEM image, because it can tell you the crystallinity. So that's the power of TEM characterization. It can tell you right away. So on the other hand, if you recall the difference between your TEM and SEM, SEM cannot tell you this. SEM you akan nampak macam layer A on layer B, but you can't see the or any particular lattice arrangement, right? That can only be obtained by TEM characterization. So that's why TEM, kalau you hantar satu sampel, it can be up to 400 plus, 500, 600 per sample yang kecil tu. Kalau you punya FIP sampel, you hantar satu, so it will probably cost you 500-600 per characterization. On the other hand, SEM will probably cost you 150-200 per characterization, right? Due to the strength of the TEM. So, yeah, the very same thing, but then this one is illustrated. Okay, illustrated is the same representation to show that you have amorphous silicon dioxide, random arrangement, therefore amorphous, on a single crystal silicon, right? Very same as this page. Sama. Right. So now let's look at how many factors affecting the oxidation process. So there are factors which could affect the thermal oxidation process. So one is temperature at which you run the process. So the lower or the higher will actually give you different oxidation rate. The second one is ambient type. Either you're running with dry oxygen as your oxidant or water vapor as your wet ox process, or you also include HCl in the process. The third one is ambient pressure of the process. So the higher the pressure will actually lead to a certain mechanism that will drive the oxidation rate to be different than the lower pressure. Substrate doping as well will also affect your oxidation process. Substrate doping here means the doping level of your silicon wafer. So in comparison to 10 to the 16, 10 to the 19 will give you different oxidation rate, therefore different oxidation thickness, despite similar other parameter settings. Okay, and finally substrate crystallographic orientation. So we've discussed last time, if you run 100, 111, 101, so they will actually give you different oxidation rate and therefore different thicknesses of your oxide. So now let's look at effect of high doping concentration. So if you're comparing your wafer doping of perhaps 10, 12, 10, 14, 16, 18, 19, or degenerate silicon, you will see the effects. So dopants in silicon increases oxide growth rate. So the higher the doping level, the higher the growth rate. So if you compare yourself with another process which utilizes lower doping level of silicon, so you're going to end up with higher thickness in comparison to the lower doping. Okay, so during linear stage of oxidation, n-type dopants increases growth rate. So if you're talking about n-type, so you're going to have the higher growth rate, particularly in the linear stage of your oxidation process. So yang mula-mula your earlier part, your phase 1, before it turns into parabolic. Dopants cause internal differential oxidation as well. So results in formation of steps affect etching process. So kalau you ada, so later on you will see throughout the fabrication process, there'll be some processes which use selective doping. So maksudnya you ada wafer, so you tak dope blanket throughout the surface with higher doping. So for example, kalau you ada wafer with 1014 as your starting substrate, so you don't dope blanket 1016 or 1017 on top. So you might leave your wafers with 1014 here, and then this region maybe 1018, and then this one is 1014 as the original starting wafer. So in that case, you will experience higher oxidation rate on the regions which have higher doping level. So maksudnya kalau you ada 1014 here, 1016 here, 1014 here, this one will experience higher doping, a higher oxidation rate, and therefore you will end up with slightly higher thickness in this region in comparison to this and this. Okay, so it's caused by differential oxidation effect. So maksudnya diikut region yang you dope lah. So the higher the doping level, the higher the oxidation rate. For example, so this is the illustration of what I explained just now. So, so if you run your process, say you run dry oxidation at 900 degrees C, if you talk about oxidation rate as a function of phosphorus concentration, so your B over A and B is the constant that we have discussed during your Dilgrove model. So still recall yang mana, still remember yang mana yang belongs to linear stage and yang mana belongs to the parabolic stage, B or B over A. So which one belongs to linear stage, B over A or B? Tengok dekat graf atas ni, micron per minute, micron squared per minute. Okay, yang mana belongs to the first one, first stage, linear stage? Is it B over A or B? Which one? Zureti, which one? Which one belongs to the linear stage? B over A or B? Ishin. What do you think, Ishin? B over A is linear, right? B over A is linear. B is parabolic, okay? You can tell by the unit, right? Micron per minute, micron squared per minute. Okay, so highly doped silicon has more vacancies. So kalau tengok dekat bawah ni, left, bottom left. So yang tadi saya explain kan dekat saya punya telefon tu. So you have heavy doping in the central region. Then you maintain your original doping on the left here and on the right region here. So assuming your N is 1014 maybe, then your N plus is 1017. So if you do your oxide growth, so you're going to end up with slightly thicker oxide in the central region because of the higher growth rate in the heavily doped region. Okay, so you akan dapat something like that. Structure dia tak sama, you punya oxide tu akan jadi bumpy in the central region due to the heavily doped beneath the region. Okay. So you can actually manipulate this for the advantage of the process or device. So let's look at another factor. Another one is called substrate orientation. So we've discussed about 111, 100 last time. So we have seen that 111 has the highest pack of atoms at the surface. So kalau you tengok the first graph ni, top left, so oxide thickness against different orientation, 100, 101, and 110. So 100 has the highest oxidation rate, therefore highest oxide thickness. 110 has the intermediate one, and 100 has the lowest one. Okay. Then how come most ICs are made with 100 silicon? Kenapa kita pakai 100 silicon for your integrated circuit? So if you plot the log on the right hand side, yang tadi tu, 111 will give you that trend, 100 will give you this trend lower than 111. Okay. On 111, more bonds are available because of the higher packing. Oxide growth faster on 111, so more silicon atoms are available on 111 in comparison to 100, therefore higher oxidation rate. Okay. So kalau you masuk dalam furnace 111 wafer and 100 wafer set at 900 degrees C, 1 hour, other settings are the same, so you're going to end up with higher thickness of oxide on 101. And wet or dry process. So this is 100. So if you look at, okay, let's look at this process now. If you run a wet oxidation process at 1000 degrees C for 1 hour, what will be your oxide thickness? Okay, let me repeat. So you run your process using a 100 silicon using 1000 degrees C, wet oxidation for 1 hour. What will be your oxide thickness? Tengok dekat chart tu. So now you tell me what's your oxide thickness after the process, assuming everything goes according to the flow. Okay. So berapa thickness you dapat? 1 hour process, 1000 degrees C, wet process. What will be your oxide thickness on your silicon 100? Right, anyone? Simple je kan? Reading the graph and that's it. No analysis required. Izian, berapa you dapat Izian? 1 hour, 1000 degrees C, wet process, 100 silicon. What do you get? How much is your thickness? Berapa? 0.2. 0.2 micron. So where is 0.2? So here's 0.2. Really? 0.2? Are you sure? 0.7? For Ika, 0.7. Izian got 0.2. 1000 degrees C, 1 hour. Come on, guys. 0.7 for Ika. Where's your 0.7? 0.2, 0.3, 0.4, 0.6. No. 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Really? 0.5? 0.5. Inas 0.5. Amira 0.5. Izian. Ilham 0.5. Okay. Faika 0.75. Farah 0.5. How do you read 1.0? 0 here, go up, go up, go up, 1000 wet process. Can you read the scale? Really? You can't see the scale? Tak nampak lah sebab nampak. Okay. Okay, hold on. 0.5. So where's 0.5? Here, right? 0.2, 0.3, 0.4. So 0.2, 0.3, 0.4. Yeah, 0.4 maybe. 0.4. 1000 degrees C, right? So about 0.4. Kalau nak tepat kena tengok you punya lecture note nanti lah. Betul tak membaris kat situ. Okay. So if it's 0.4, then you're going to end up with 0.4 micron or 400 nano or 400 nano or 4000 angstrom, right? 400 nano or 4000 angstrom on your silicon by wet process. So that's considered thick, okay, quite thick. So let's look at, if you run the very same parameters, 1000 degrees C, dry process, 1 hour. What do you get? 1000 degrees C, 1 hour, dry process, what do you get? Tak apalah, tak nampak tepat pun, at least you dapat the magnitude. How much? 1000 degrees C, 1 hour. What do you get? Dry process, same orientation. So must right 1000 degrees C, you go up there. Yup, it's 007. James Bond 007. It's not 0.1. It's not even 0.1 yet. 0.2, 0.3, 0.4, 0.5, 0.5, 0.6 maybe. Yep. Okay, so it's 005, 006 in comparison to 0.4, 0.5 for dry versus wet at the same temperature. So it's due to the different growth rate of wet versus dry. Kalau you compare same temperature, same substrate orientation, everything else is the same. So it can be one order of magnitude difference between dry versus wet process. Okay. Dulu pernah naik soalan ni dalam final exam sebelum ni. Final exam 487 last 2 years I think. Or in fact last year as well. Baca graph ya. Graph is simple. It's a simple learning process. Tapi unfortunately dalam exam ada student yang salah juga baca graph. Tadi you cakap tak apalah, you tak nampak scale and everything. Tapi dalam the exam paper where you can see the scale clearly, still ada student yang give me the wrong answer. You don't have to analyze anything. Just letak pembaris, tengok dapat berapa, and that's it. Write down and you get 5 marks. Can be as simple as that, and still something's wrong. Okay, so if you compare with 111 now, so kita tengok wet process, 1000 degrees C, 1 hour on 111. So what do we get now? You go up there, 1000 degrees C, wet process, so it's slightly thicker than the 100. Slightly, yeah, tak banyak. Okay, thermal oxide charges, potassium, like potassium charge K plus, sodium charge Na plus, they are all mobile charges. So charges are detrimental for your oxide process because you wanna create an insulator layer, but if you have oxide charges, mobile oxide charges, so they will be detrimental because they will counter the effect of your insulator. Okay, so there'll be oxide trap in the layer as well. If you're talking about a very thin layer of oxide, sub 10 nanometer, so below 10, so having these charges will be very, very dangerous. High pressure oxidation, so another effect is due to the pressure. So atmospheric pressure, it will slow down your growth rate. So if you increase your process pressure, if you like, process pressure, so it will also increase your oxide growth rate. So if you run your process at a higher pressure in comparison to atmospheric, for example, so you're going to end up with a thicker oxide by the end of the process. Increasing pressure allows temperature to be decreased. So you have a margin there. We have learned that from previous. Increase the thickness here, for example. No, not the thickness, the temperature. Yeah, 900 is here, 1000 is here, 1001 is here, 1002 is here. So kalau you increase the temperature, you're gonna end up with higher growth rate, therefore higher thickness, and you also have pressure to play with. So if you run at higher pressure, you're also gonna end up with higher thickness due to higher oxidation rate. So bila you ada dua parameter tu, you can actually play around with those. So if you can run higher pressure, you can actually reduce the temperature a little bit in order to deliver the same oxide thickness. So you can play around. Or if you want to run at higher temperature, you can reduce your pressure a little bit in order to deliver the same oxide thickness as well. So it's like playing with the trends that you already know on your process. So dry thermal oxidation, pressure in oxidation tube is increased. Wet thermal oxidation, steam pressure introduced into the oxidation tube is increased due to the bubbler. Okay. Kalau kita dry ox, they increase dia punya pressure due to the gas, incoming gas. So high pressure oxidation, these the equations related to it. The oxidation temperature can be reduced if the pressure is increased to achieve a certain oxidation rate. So just like what I said now, you can actually play around with your pressure or temperature, vice versa. Satu increase, satu decrease, in order to deliver the same oxide thickness. So this is the graph to show the effect of the pressure, if you like. On the left hand side, it shows higher pressure, 1 atm is the lowest one, 1 atmospheric pressure. So 5 atm, 10 atm, 20 atm. So if you run your process at 900 degrees C, for example, for this particular chart, at 1 atmospheric pressure, you're going to end up with about 0.1 something, sorry, 1.0 something kilo angstrom. So that's 1000 angstrom or 100 nano. On the other hand, if you run at 5, say 20 atmospheric pressures, you're going to end up with 10 kilo angstrom, 10,000 angstrom or 1000 nano. Okay, 1 order of magnitude if you run 1 atm compared to 20 atm. So you can also add chlorine species with the oxidant during the process. Okay, you can also run with chlorine added to your process. So chlorine species, the examples are anhydrous chloride, Cl2, HCl, TCE, TCA. So what's going to happen is your oxide growth rate increases, your oxide will also be cleaner, and device performance is improved. So you have to add your chlorine species along with the oxidant to ensure a better process. So what is actually doing is introduction of halogen species or chlorine species with the oxidant. So for example, if you add 1 to 5% of HCl or TCE to your oxygen precursor, so it will help to reduce your metallic contamination in the device or in the oxide layer. So as I said just now, if you are running a very thin oxide, sub 10 nanometer oxide, so your oxide integrity or your oxide quality is very, very crucial. So therefore, you don't want to have metallic contaminants at all in your process or in your oxide. So having contaminations in your thin oxide will of course be detrimental to your device. So adding chlorine species will also help to improve SiO2 and Si interface properties. So we know that your sodium or potassium ions are mobile in the oxide layer. So by having chlorine here in the equation here, M plus Cl, M is your metallic contaminant, either it's sodium ions or your potassium ions. So it'll be reacting with a chlorine species to form MCl, a compound that can be removed after the process. So therefore, you have managed to remove your mobile charges in the oxide layer. Right, another scope of the oxidation process that is beneficial for you to know is called low-cost process or local oxidation of silicon. So where you can do the process of, you can do the low-cost process. It's not low cost, it's low cost, local oxidation of silicon. So it can be done like this. So you have your silicon in gray color here, and then you blanket you deposit or you grow your oxide blanket on your silicon, and then you have your nitride layer there, and poly layer there. Okay, you have the nitride as the features on the left and on the right. So what happens next is you send the sample with these layers into your oxidation furnace. So what's going to happen is the exposed layer will be oxidized like that. Okay, then dia akan form bumpy punya feature dekat tengah tu. Okay, then you etch your nitride, your silicon nitride on the left and on the right will be etched. So you'll be left with silicon dioxide on silicon like this, bumpy feature. So it's called low-cost process, local oxidation of silicon. So 100 angstrom or 10 nanometer of silicon dioxide pad oxide to release mechanical stress between nitride and silicon. So this is what we do in order to relieve the pressure of nitride and silicon. Nitride is of oxide on silicon, and to be able to peel off kan dia you pakai pressure punya konsep by doing low cost. Okay. So another representation of the low cost process, same thing. So you have your oxidant acting on silicon. So you have your nitride blocking the silicon during the low cost process. So you end up having thick oxide on the silicon versus a very thin layer of oxide under the nitride, and the nitride will be mechanically forced, if you like, away from the silicon and eventually peel off and completely remove from the oxide. So how many more pages do I have? Dopant oxidation. Yep, I think I'm just gonna stop here. We're gonna cover dopant redistribution tomorrow. So for your information, when you do the thermal oxidation process, you're gonna experience dopant redistribution during the process. So just now I showed to you that in some cases we might have some dopants already on the silicon, and then we go for the next oxidation process. So the silicon wafer is going to experience dopant redistribution during the process due to the high temperature effect. So apa akan jadi during dopant redistribution ni kita akan cover esok. So you're going to see that there will be slight change in the distribution of the dopant after oxidation. So you have to know what's actually happening so that you know what's the implication to your original dopant concentration and original dopant profile after the process versus before the process, so that you know what you're working with after the process in order to proceed the fabrication processes before you complete the device. Okay, so that's it for today. Any questions? Okay, so far on the effects of different factors towards thermal oxidation process. All good? No questions? Ada? So far so good. All right then. So I'll see you tomorrow, inshallah. Bye-bye. Take care. Assalamualaikum. Have a nice day, you too.